My name is Bianca Nicholas, and my research tests the influence of temperature on the concentration of hemoglobin in different earthworm species, the Lumbricus terrestris and Eycina foetida erythrocurins. The leading cause of potentially survivable deaths in combat is hemorrhage. This is commonly due to the shortcomings of safe, ready-to-use, donated human whole blood, along with the strenuous limitations of war zones. Soldiers are oftentimes restricted to supplies carried on hand, lugging them through difficult terrain. On top of this, donated human whole blood demands cold storage conditions, blood typing, and more. Debilitated soldiers in need of blood can't wait these extended periods of time for the processes to take place. The rejection of whole blood used for transfusions can determine the outcome of these life-or-death situations, and hemoglobin-based oxygen carriers, HbOCs, a type of artificial blood substitute, can offer a safer, faster alternative to combat the preventable fatality rates in war zones. HbOCs can relieve most, if not all, of the shortcomings of donated human whole blood, being that there are no specific storage requirements, immunologic reactions from blood typing are avoided, and by offering a faster source of blood oxygen. However, being that HbOCs are pure hemoglobin (Hb) solutions derived from expired human and bovine red blood cells (RBCs), there is no protective RBC covering keeping the oxygen-transporting protein, a tetramer, made of two alpha and beta subunits. This causes the solution to rapidly dimerize when entering the bloodstream, binding with nitric oxide, forming toxic nitrate that causes systemic vasoconstriction and nephrotoxicity. Although different types of Hb, or erythrocurins, can have different results. That of the common earthworm, the Lumbricus terrestris, offers a unique perspective, being that it's extremely stable, resistant to oxidation, and is comparable to human whole blood in how it transports oxygen throughout the cardiovascular system. Not only can different types of Hb alter the performance of this technology, but externalities like temperature can also affect human Hb in respect to its concentration. But how can temperature be used over time to change the same aspects of different earthworm erythrocurins? The goal of this research is to see how temperature can be used to modify the performance of Hb in two different earthworm species, the Lumbricus terrestris, LTEC, and Eycina foetida, EFEC erythrocurins, to limit the risks of HbOC toxicity and replace the use of donated whole blood in war zones, combating the preventable fatality rates by following the question, to what extent can the manipulation of temperature influence the concentration of Hb in Lumbricus terrestris and Eycina foetida erythrocurins? The hypotheses include warmer temperatures resulting in increased concentration, while LTEC will be less influenced, being its current strong resistance status. To test this, an experimental statistical analysis was performed where two samples of each erythrocurin were placed in thermoregulators ranging from 5 degrees Celsius to 35 degrees Celsius in reference to the controlled room temperature sample. These samples were then diluted and measured on a scale of absorbance v wavelength with a spectrophotometer after about a month, because patients with anemia and hemorrhage typically see changes in Hb concentration during other Hb-targeted therapies after about 4 to 6 weeks. After the first measurements, the samples will then be placed back into their respective incubators and re-evaluated on the same scale after another month to demonstrate superiority over the 42-day shelf life of donated whole blood. Frequent pictures will be taken to document any oxidation in the form of color change and protein aggregation, as seen in the pictures on the right, making note of increasing aggregation and darkening color within one of the test groups. The graph's integrations were compared and related back to concentration, finding that, on average, the warmer temperatures had higher absorbances and therefore higher concentrations. However, after 2 months, the total average concentration started to decline for all test groups besides the coldest 5 degrees Celsius test group. The integrals for the first month supported the claim that concentration increased as temperature increased within both erythrocurin samples. To test the strength of the correlation, points from 625 nm to 650 nm were placed into a line reg AX plus B command for the correlation R coefficient, being that within this range, all absorption points were below 1. This proved the data to be statistically significant, with no R value dropping under negative 0.95. A clear and direct negative relationship was found, unlikely to happen by chance. At the 2-month mark, total average concentration began to decline. However, that of the coldest 5 degrees Celsius test group exhibited an increase in concentration, while the warmer groups seemed to have started the overall decreasing. These relationships were also extremely strong as proven by the correlation R coefficient. The experimental results showed that total absorbance tended to be greater as temperature increases, but an inverse effect seems present with prolonged incubation time. It can also be concluded that EFEC had greater concentration resistance, but greater protein aggregation, while LTEC displayed a greater visible color change. This proves that temperature does have a direct relationship with the HB of different earthworm species, and incubation time greatly influences how applicable the changes can be. To further support the newly found relationship between earthworm HB and temperature, a wider and more specified temperature range with more samples and trials of each type of erythrocurin should be utilized. Having a known calibration curve used in the data analysis process would directly align the findings with the Beer-Lambert law of absorption and concentration to produce a numerical concentration value to further support the conclusions drawn. The irregular shapes of the samples can lead to a less precise rating with greater room for human error, so the numerical value can offer a concise and accurate representation of the concentration of HB within the erythrocuorins. This direct relationship can affect the real world by expanding the construction of HBOCs to use different earthworm erythrocuorins as the main source of HB, being that they can be further modified by temperature and incubation time to better fit the conditions experienced in more zones. These findings add support to the claim that temperature can influence hemoglobin, but it also offers the new understanding that earthworm erythrocuorins can undergo similar changes. This also starts the conversation of how incubation time can influence the already known resistance and stability of earthworm erythrocuorins. Because EFEC better withstood temperature fluctuations over time, this type of hemoglobin can be applied to HBOCs for use in war zones, offering their higher resistance to different externalities, giving soldiers the faster and safer blood alternative they need. By expanding the use of earthworm erythrocuorins, like that of EFEC, in HBOCs and other artificial blood substitutes, these preventable hemorrhage and blood loss-related fatality rates in combat can be better controlled by accommodating to the environment around them, something that donated human whole blood can't effectively achieve. Thank you for your time.